So in this video, I will show you how we can use the Ampere's law to find the B field especially from the magnetized object or material with the inherent or permanent frozen in magnetization M. So let me briefly review the Ampere's law. So when we have the current density J, and this current J will generate the B field. Okay. And these two physical quantities should satisfy one of the Maxwell's equation. With J. And if you further derive this equation mathematically, then you can find for any arbitrary closed loop C, we call this Amperian loop in this some direction. Then you can do the line integral of the B field along this closed loop C, and it always equal I enclosed. Okay? So I enclosed means that the total current flowing through this area enclosed by the your loop C. And in the previous videos, I introduced the current vector I, so current as a vector. And here we need the magnitude of the vector, the scalar vector I enclosed. So from the vector current, we can define this scalar vector I enclosed to be vector current I enclosed dot product NC hat. And here NC hat means the normal vector N of your Amperian loop C. So whenever you have loop C, and when you have clarified the direction, you can define the closed loop C. You can define the normal vector to that closed loop C using the right-hand rule. I want to remind you that I explained this in detail in the other video, but I remind you that when you have volumetric current density, then if you measure the current over this cross-sectional area S, then vector current I equals double integral of J over this area S. And when you have two-dimensional current K, and when you measure, if you want to measure the two-dimensional current from the surface current density K, you have to set the cross-section. And this cross-section of a seed will be a line. Okay? And the current is obtained by K dl capital L. So the current I, vector I, will be obtained by the line integral of the surface current density K. So let's solve an example question. Suppose we have infinitely long cylinder with a radius r. So here's the z-axis, and we will use the cylinder coordinate system S. Radius is r. And let's say we have magnetization M. So this cylinder is already magnetized. So So even without external B field, it has a permanent or inherent frozen in magnetization M, which is given by KSCF. So it means that magnetization is very weak along the z-axis, but it's getting stronger and stronger, and strongest at the edge, near the surface. And what we want to do is that we want to find B field both inside and outside. Okay. And our strategy is that here first we want to find from given M, we want to find the KB and JB bound current, and then we will find the B using the Ampere's law. So let's do the first step. So JB is given by the curl of M, and here in the cylindrical coordinate system you can find this online. Okay, and now we know that the M is only has a z direction, so mz ks, and round this g equals k, and everything is 0. Okay, so now you can see only this term, round mz over round s, will survive. So jb equals pf. And kb and let us curved surface, the side surface, and m equals ksg, and the normal vector n, right? This is normal vector n, equals SA. So we found JB and KB. And JB is inside and KB is the surface. So if you look at the top view, we have a circular cross section of the cylinder, and inside the cylinder, the JB is rotating minus K phi. Rotating. This is JB phi. And at the surface, it is flowing the phi hat direction, plus phi hat direction. So we have this type of rotating current along the z-axis infinitely long cylinder. Okay, so we will find the B field from this current distribution using the Ampere's law. So when you use the Ampere's law or Gauss' law for the electrostatics, the first step you should do is you have to um, simplify your unknown function B field, vector field as much as possible using the symmetry given in the question. So in this case, so to do that, the B field in this cylindrical coordinate system will have three unknown functions in most generally. You can use different names of the function if you want. It doesn't matter, it's just naming. And so you have three unknown functions to clarify the B field in the space. And each of these unknown is a three-dimensional scalar function, right? And it has the S and phi and Z dependency in general. So it's very complicated, and you cannot use the Ampere's law on this complicated general unknown functional form. So you have to simplify this first before you think about the Ampere's law. So you need a little bit intuition here, but you can ask yourself two questions. First, how the magnitude of B field will depend on S, V, or Z, or all of them. And second question is, what will be the B field direction? As SA component or PF component or ZF component or everything, okay? You have to ask yourself, given the symmetry. So in this specific case, we have a circulating or rotating current, right, along the z-axis. So if you think about the dependency first, this infinitely long cylinder, so the B field will not depend on Z first. It's very easy, right? Because the system has a symmetry along the Z-axis. So even when you measure the B field at different Z value or different height, it will give you the same magnetic field value. So it will not depend on Z. We can exclude the possibility of the dependency on Z. In the same manner, it will not depend on phi, isn't it? This cylinder has a symmetry along the angle, okay? So in other words, it has a rotational symmetry. So even when you measure the B field at the same distance and same height but different angle around the cylinder, it will give you the same identical B field measurement. So it will not depend on P. And let's think about S. Maybe it will depend on S because if you measure the B field from this current distribution very close to the cylinder or very far from the cylinder, the B field will be different. B field will be weaker and weaker if you measure the B field from farther and farther from the cylinder. Right? So we think S should be here. And now we have a little bit simpler form, but we still have three unknown functions, Bs, Bphi, and Bz. So let's think about direction of the B field. And it's a little bit more tricky, but now we have a kind of rotating current. Okay? And if you use your right-hand rule and think about something like a solenoid, the B field would not have a rotating B field in this case. Okay? Because B field is generated around the current direction, and current is kind of now rotating along the phi direction, so phi hat direction, so B field will not have phi component. And radial component is a little bit tricky, but if you think about solenoid, all the radial component will be cancelled out because this cylinder is long, infinitely long, so the current loops along this type of solenoid, like current distribution, the radial component of B field will be cancelled out. So we will have only z hat direction. So you can think this will equal 0, this will vanish, and we have only bz, okay, and z hat. So you can simplify. Let's take out the z because we have only one. So now it's much simpler, and you can focus on finding this single unknown function bs, okay, using the Ampere's law. And we also want another condition here is that, as I mentioned, when s goes infinite, the field field will become 0 because it has a finite quantity distribution in the radial direction. So if you go really far from the cylinder, then it will become 0. So we will use these two kind of simplified functional form of the unknown function and the condition of the B field, asymptotic behavior of B field at the infinite distance. And in the second step of using Ampere's law is to draw the Amperian loop. There are many different ways of drawing Amperian loop, and there's no absolute guidance. But here's a tip. I mean, it will make your job easier if you draw an Amperian loop such that the loop, Amperian loop, is parallel to the B field direction you expect. So here you expect the B field will have a z hat direction. So your Amperian loop, or at least a segment of your Amperian loop, should have z hat direction. So for that, let's think about the side view of this question. So it says z hat. Yes. And we have a cylinder, this. The radius is r. And we found that the current is if you look at the previous figure I drew, the volume current is flowing inside the cylinder along the negative p hat direction. So it should be come out. Right? And we have the KB around the surface with the direction plus p hat, which means that goes into the screen. Okay, this is KB. And as I said, we expect the B field will have a z hat direction. So let's try to find a B field, but we have two different regions in this question, like a Gauss law problem. So we will define outside and inside. Okay. We will apply the Ampere's law separately for these two regions. So region 1, outside. We have to draw the Amperian loop first, and it's a little bit tricky, but let's draw the Amperian loop. This is a rectangular shape. Okay, and we have a direction. And length is L. and this position is S, this position is S1. Okay, so S is a variable and S1 is another kind of variable to represent the position of the right hand side segment of your Amperian loop C. So this is C1. So left hand side of your Ampere's law is the line integral over C1 dr. Okay, and B has the z direction. Okay, so the horizontal segment will give you 0 for this line integral. So only you need to only consider the two vertical segment of the C1, and the first segment will give you L, okay? And the next segment, the right hand side segment, will give you negative PS1 times L, okay? And right hand side is the mu naught C, and there's no current here, right? There's no current flowing through the area, this green area enclosed by the C1, so this becomes 0. So it means that Bs equals Bs1 for arbitrary any S and S1, as long as they are larger than the radius capital R. So it means that the magnitude of the B field is a constant, is a uniform outside of the cylinder, because we expect that the B field will be 0 at the infinite, and B field will be uniform, okay, outside the cylinder, so it will become 0 for any arbitrary S is larger than the radius R. Okay? And let's look at the second region 2, and you can draw the line along the like this. Okay, so this is the another length L, and here is the S1 means S. You can apply the Ampere's law on this C2. So left hand side of Ampere's law will become Bs L minus Bs1 L, right? In the same way, and right hand side should be mu naught I, E, and C. And here we have two types of current, right? Red current and blue current. So you can think about the current vector first, and this will be you have to consider both current types, JDA, KDL. And we have the area integral along this green area of the closed by C2. So the J is the negative KP hat, and we found JB here. Sorry, JB here, and the area integral will be, this is on the SZ plane, right? So ds dz, and the range of the S from S to S1 to S to R, because the current the blue current only exists from 0 to R, and we are doing area integral from S to S1, so the area integral range should be from S to capital R. And for Z direction is from 0 to capital L, the length, and then K will be from 0 to L, KR, V, that was KB we found above, and line integral should be dz. So if you calculate this, so this become KLSP hat. And as I showed in the beginning, the enclosed current should be vector current times the normal vector of your Amperian loop. And if you see the Amperian loop, the direction is the if you use your right hand rule, the direction should go in. Your thumb will go into the page, which is a phi hat. So this is a phi hat. And if you plug in INC, then this will be KLS. Okay. So by equating left-hand side and right-hand side, but here you can see this S1 is larger than R, and we found in the region 1 BS1 equals 0. So you can find the unknown BS in the inside the cylinder to be mu naught. Here's mu naught KS. Mu naught KS. So we can write down the B field answer as a vector form. Inside the cylinder and 0 outside the cylinder. Okay. So if you look at this, we can find the B field from the inherent magnetization M. Okay, using the bound current concept first. So we can find the bound current first, and then apply the Ampere's law region by region, so that we can find the unknown BS and then determine the magnetic field B. But there's an alternative way. You can use the H field to solve the same question. So H field is defined by whatever you do not B minus M. Then this will give you, if you apply this to the Maxwell's equation, then the current of H is always J, but only free current. So now you don't need to worry about bound current. You only need to focus on free current, and this will give you a modified or general Ampere's law, which is the enclosed free current. Okay, so you can apply the same method for the Ampere's law. You can draw the Amperian loop, blah blah blah. But here you only need to focus on free current. You don't need to worry about bound current, which will make your job much easier. So in this case, this problem, there was no free current. So this will give you H field will become 0. Both inside and outside. Okay, and by definition, H field was M and this 0 now. So B field and 0 outside, because the magnetization M equals 0 outside, and you can see this is the same answer. So we can obtain the same answer using H field more easily. Here, of course, you are not mathematically very accurate when I conclude that H equals 0 from I equals 0. So let me a little bit more explain that. So J free equals 0 everywhere. Right? So when free current density J equals 0, then it means that curl of H equals 0, right? By the Maxwell's equation. But when a vector field has a zero curl, it does not automatically guarantee that the vector field equals 0. This is actually wrong. For the vector field to be 0, the curl should be 0 and the divergence of the field should be 0 as well. Okay, so you need two conditions. Okay, so to be more accurate mathematically here, you have to examine what will be the divergence of H in this question, and you can apply the divergence. Then divergence of H field will be like this. Okay, and then this is divergence of B and divergence of M, and this becomes 0 because there's no magnetic monopole. So this is the 0 by it's always 0 by the other Maxwell's equation. And here M was actually given. M was the KSC hat, right? KSC hat. So if you plug in this minus divergence of KSC hat, then this becomes 0, right? So now you can say H equals 0. But if you only have the curl equals 0, you cannot say H equals 0 automatically. But in this specific question, example problem, we can say H equals 0 because the divergence of H becomes 0.